Rudewright Academy. Learn it, teach it, remember it, dynamic programming. By the end of this, you won't memorize it. You'll learn to see it. You're standing at the bottom of a staircase, and you can climb one step or two at a time. So how many different ways are there to reach the very top? Count the tiny cases first. One step has a single way up. 2 steps give you 2 ways. 3 steps open up 3 ways. The pattern is sitting right there waiting for you. Here is the whole trick. Think about your very last move onto the top step. It was either a single step from the stair just below or a double step from 2 below. So the ways onto this step come from the step right beneath it plus the ways from the 1, 2 below. You just add those 2 counts together, and that is the whole recurrence. Write it the obvious way, a function that simply calls itself. It is correct and it reads beautifully. But run it for 50 steps and it makes over 20 billion calls. Something here is deeply, deeply wrong. Now draw all of those calls out as a tree. The top call splits into 2 and each of those splits again. Now look really closely at it. The very same question gets computed here and again over here. It is the same work over and over, and those repeats are the overlapping subproblems. So the first time we solve a step, we write its answer on a little sticky note. Every time after that, we don't recurse at all, we just read it off, and that whole branch quietly vanishes. The exploding tree collapses down to 1 answer per step, just 11 of them. Exponential work has become linear work. But here is the real twist. The remembering part is genuinely easy, it is purely mechanical. The real job the part interviews actually test is choosing what each subproblem should ask, which is the state. State design is the entire job. This whole thing only works when 3 things are true. First, overlapping subproblems, where the same questions keep repeating. Second, optimal substructure, where the best whole is built from the best parts. And third, a small, finite state. Miss even one of these, and it simply isn't DP. Every DP solution comes down to 3 decisions. First, write the state in plain, honest words. Then the recurrence. One choice now that leaves a smaller version of the same problem. And finally, the base case. Once the state is right, the recurrence almost writes itself. First, let us just try greedy. Make 6 by always grabbing the biggest coin that still fits. The biggest under 6 is 4, so take it, and 2 is left. The biggest under 2 is 1. And then 1 more. That is 3 coins, and it honestly feels right. But 3 plus 3 is just 2 coins. Greedy committed to that 4 far too early. So instead, we carefully weigh every single choice. The state is the fewest coins needed to make an amount. The recurrence is 1, plus the best answer over each coin of the amount left, and the base is 0 coins to make 0. Now watch DP solve the very same problem bottom up. 0 needs 0 coins, and that is our anchor. 1 needs a single 1. 2 takes a 1 plus the answer for 1, so 2 coins. 3 can take a 1 and leave 2, or take a 3 and leave 0, and 1 coin wins. 4 takes a single 4 and leaves 0, just 1 coin. 5 takes a 4 and leaves 1, so 2 coins. And 6 takes a 3, leaving 3, which we already solved, so 2 coins. Every box was built from boxes we had already filled in. The whole thing is just 3 small moves. Start with the plain recursion you already wrote. Add 1 cache line and exponential becomes polynomial. Then a simple loop fills a table from the bottom up. Watch it run, the same answers, just built in order. Picture houses in a row and you can't rob 2 of them in a row. The first 2 houses are easy. Then at every house you face the same small choice. You can skip it and keep whatever you had collected so far, or rob it and add what you had 2 houses back. Whichever is bigger becomes the new best, house by house, right to the end. Add it all up, and the most you can take here is $12. Some problems need two numbers instead of one. Here is the cheapest path through a grid, moving only right or down. Each cell is its own cost, plus the cheaper way into it from above or from the left. Fill them in order, every cell leaning on the ones before it. The cheapest path comes out to 7, and the state has grown to 2 dimensions. So how do you actually spot a DP problem? You ask 4 quick questions. 1. Are you after an optimum or a count? 2. Can you phrase it as one choice that leaves a smaller version of the same problem? 3. Is the state just a few small numbers? 4. Do the subproblems actually repeat? 4 clear yeses, and it is almost certainly DP. Almost every DP you will ever meet wears one of 4 outfits. Sometimes the state is just one number on a line. Sometimes it is 2 numbers, which makes a grid. Sometimes it is a range that you split in 2. And sometimes it is a tree. So on a new problem, your first question is simply, which of these is the state? There are 2 ways to actually write it. Top-down is the recursion, memoized, and it is the easiest to derive. Bottom-up is a table filled in order, which is faster and easier to shrink. Both give you the exact same answer. So start top-down, then switch when you need speed or memory. Finally, 4 traps to watch for. 1. A missing base case. 2. A state that is too big or too small. 3. Reaching for greedy when it simply isn't safe. And 4. Recursion too deep or tables too huge. Trace one tiny case by hand, and the bug always shows itself. You truly master this by deriving the state out loud on a whole ladder of problems. Climbing stairs, then house robber, then coin change, and onward and upward. Say the state first, every single time, until you see it before you have even finished reading. So dynamic programming is just recursion that remembers. It works on overlapping pieces with a best from best structure and a small, clean state. The whole art is really in choosing that state. So name it, solve it once, and write it down. Want to keep learning? Come find us at academy.rudewrite.com.